Okay, I'm here to talk to you about energy level diagrams and electron energy in general. You can find a lot of this on page 3 of the physics reference table. There's a whole page dedicated to this, and it's really a much smaller unit than many of them, but you'll see the page that looks like this is dedicated to it. And I've recreated a little bit of it on just the top of the page, I guess, as a hydrogen energy level diagram here. But I really want to encourage you to pause the video and get out your reference table if you have it with you, because it'll make everything a little bit easier to understand if you can just reference the reference table. Energy level diagrams. We've probably seen some equations, or if not, we will soon, about the energy of a photon. So a photon is just a particle of light, and we can figure out its energy using this Planck's constant times its frequency. And the higher the frequency, the more energy. You also have the hc over f, which is basically rewriting this equation using frequency as velocity over wavelength, knowing that the speed of light in a vacuum is c. So E equals hc over wavelength. Another equation we're going to use is directly related to this is the energy of a photon is equal to its initial minus its final energy level. And that comes from this table here. So let's think about this. This is based on the Bohr model of an atom. And it's not entirely the best model of an atom, but it works really, really well for energy level transitions. And you might have seen some of this in chemistry as well. But the idea is this, is that atoms have electrons in orbit around them, and they have different energy, or different levels in which they reside. So this would be level 1, level 2, level 3, level 4, etc., etc. And if electrons are, and they're limited to a certain number of electrons in each orbital shell, that sort of stuff, an electron can move from shell to shell, but it has some sort of energy to do so. So if it's in a low level, like on n equals 1 level, it can jump to a higher level if it absorbs some energy. And that energy usually comes from a very specific color of light. So it absorbs a very specific amount of energy. And when we talk about energy in this, we're talking about very minuscule amounts of energy. So we're not using joules, we're actually using electron volts here, EV. And you'll find a conversion to electron volts on the first page of your reference table. So electrons will absorb some energy that is a certain color of light, hits them, and they will jump to a higher level. If they gain enough energy, they can be ejected from the atom altogether. That's called ionization. So there's a limit to how much energy they can absorb, because at some point they're going to be ionized and they're just going to kind of run away from the atom. They can also drop from a high energy level to a low energy level, and when they do that, they give off energy. So it's almost like a form of potential energy that they're gaining as they go up here. When they drop to a lower level, they emit energy, and that energy comes out as very specific colors of light. These are atomic spectral lines that we will see. So it absorbs spectral lines for this, and it emits spectral lines for this. And if you want to look and see exactly how much energy it absorbs, you can look at these energy level diagrams. This is one for hydrogen. There's a separate one for helium. You'll notice that they get spaced out the further they go. So the biggest jump is always to go from n equals 1 to n equals 2. Well, the biggest jump is between n1 and n2. Now you can jump more than one level. You could go from n1 to n3, you can go from n1 to n4, you can go from 4 to 3, you can go 4 to 2, you can go 4 to 1. There's lots of different options. N equals 1 is called the ground state. It's the most stable location. And if you go out to n equals infinity, that's called ionization. That's at the point where that electron is just completely gone. If you haven't paused and written this down, I encourage you to do so, because I'm going to erase some of this in a minute. And there goes Bohr model right there. And so let's think about these transitions. Let's start with a simple, like, say you have an electron in n equals 3. And we want to figure out what kind of emissions it will give off as it drops to n equals 1 and emits light. And typically you might be like using something to energize some of these electrons. So you have a few options. It can go from n equals 3 to 1 directly, but could also go from n equals 3 to n equals 2, and then drop down from n equals 2 to 1. So you have three different possibilities about what could happen. Now, sometimes you'll know that it goes from 3 to 1, and you can figure out how much energy that is. Sometimes you will not know, and you might be asked how many spectral lines if you have transitions up to the n, from the n equals 3 level to the n equals 1 level. So from 3 to 1, you can have up to 3 spectral lines, depending on how that transition goes. If you want to figure out how much energy is given off, you do this equation, E initial minus E final, keeping in mind that the energies are all negative. So from the 3 to the 1 level, final is negative 13.6, initial is negative 1.51, so you end up getting E equals negative 1.51 minus negative 13.6. For this one, E equals negative 1.51 minus negative 3.40. These are all on electron volts, eV. That's the 3 to 2 level. The 2 to 1 level is equal to negative 3.40 minus a negative 13.6 electron volts. And so if you put this into your calculator, you will actually get the energy 1.51. Now you'll notice that this is subtracting a negative, so you end up with a positive energy of 15.11 eV. Here you get an energy of, okay, that's not right because I made a mistake, because I had this off by a negative. A positive 12.09 electron volts. Here we have 1.51 negative 1.51. Which equals 1.89 electron volts. And here we have 10.2 electron volts. So 3 possible transitions, 3 different values for the amount of energy they give off. And this energy comes out as light, and that light has a very specific color to it. And that's the point at which you can start looking at these equations right here. You can figure out the frequency of the light, for example, knowing the energy, because the frequency will be energy of the photon divided by h. Now the tricky part is now you start having to figure out what kind of units you have. Sometimes you're going to keep them in electron volts. Sometimes you're going to switch units. And you want to make sure that the value for Planck's constant, h, is the right value, and that would be on the first page of the reference table. And so if you're ever unsure, an electron volt, or h, is equal to 6.63 times 10 to the negative 34th joule seconds. So that is your Planck's constant right there. Now they do have equations to convert directly from electron volts to joules. So we could do that if you want, because Planck's constant's in joules. So let's just take the simple 12.09 eV. And we say 12.09 electron volts. Now we want to convert from electron volts to joules. So we want to get rid of electron volts. We want to go to joules. We look at the first page of the reference table and we see that 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. Multiply those two, see what we get. 0.09. And obviously it's going to be a very small number. 1.93 times 10 to the negative 18th joules. Very small, which is one of the reasons why we work in electron volts sometimes, because you're dealing with such small values of J. Now let's say you want to find a frequency this corresponds to. We know the energy so frequency is just E over H, which in this case would be 1.93 times 10 to the negative 18th over our Planck's constant, 6.63 times 10 to the negative 34th. That's joules times seconds. So our frequency is going to end up in units of 1 over seconds. That's good. That's a hertz. 1.93 E negative 18. Be careful when you use parentheses in this, like you want to make sure you don't make a calculator mistake here. 1.93 times 10 to the negative 18 divided by 6. I use this the E button, like the double E button, because it makes it a lot easier to not have to worry about parentheses. So that gives me a frequency of 2.91 times 10 to the 15th hertz. So we have now just correlated an absorption. We figured out how much energy it was in electron volts. We've changed that to joules, and now we've figured out what the frequency of that is. 2.91 times 10 to the 15th hertz. It's a pretty big frequency, but we've looked at frequencies on the reference table before, and we can look up on page 2 and see what that is equal to. Now, violet is in the range of about 7 times 10 to the 14th hertz. So this is a higher frequency than violet. So you're looking right now in the 15th hertz, you're looking at ultraviolet. So this is somewhere in the ultraviolet range. But remember, this was the n equals 3 to n equals 1 range. That's a pretty big jump. If you go from n equals 3 to n equals 2, it's a lot less energy, and therefore it's going to be a lower frequency and probably in the visible range someplace. And n equals 2 to n equals 1 was also smaller. So they're going to emit sometimes in visible light, and sometimes they're going to emit in non-visible light. You can reverse this whole process, and you can look at how much energy it absorbs if it goes from a low level to a high level. It's the same exact process. The only difference is that your energy is going to become negative because it's absorbing energy. This time the energy is positive because it's emitting energy. It's giving off energy as it drops. I think that about does it for this video. Thank you very much for watching.